Thank you. It's a pleasure to be back at KITP. I think, yeah, I've not been here since the pandemic, so it's lovely to be back, and really great to just chat with all of you in person about all of your exciting science. So the program that I'm here for is called Building a Physical Understanding of Galaxy Formation with Data-Driven Astronomy. So a little bit of a mouthful. And so my title here is how do we learn about galaxy formation in this real data-driven era where we have billions of galaxies with lots of multi-wavelength properties. Of course, not just galaxies we can observe, but also gas and other things in the universe. And so my goal in the next 45 minutes is to basically try to set the current context of galaxy formation as I think about it personally, but also in particular in this context of where we are with getting all of the information possible out of very large astronomical data sets that I would say we already are facing this challenge, but we are definitely going to be facing it a lot more in the next decade or two than we have been. And we are going to need to do a lot so that our models and our tools can keep up with the information that's available to us. So just starting with the very biggest picture about galaxy formation, sort of, you know, what are the physical processes that set galaxy formation, that drive all of the properties of galaxies, their spatial distribution, how that evolves over time. How do we combine lots of complex data sets to get physics out of it? And I think a particularly interesting part of galaxy formation is that there's really two communities that care about galaxies. There are the people who really care about galaxy physics, and there are the people that care about using galaxies as a tool to learn about other physics, like, you know, the expansion history of the universe, the matter density, what the nature of dark matter is. And those communities are overlapping, but they're relatively distinct. I don't actually think we can fully separate these. And I personally work at the interface. But that's part of what makes this a hard problem. That we're really talking about a very complex, multi-scale problem that goes all the way from, you know, the physics of the ISM to, you know, the structure of the entire universe that might tell us about, you know, the earliest moments of inflation. So that's the challenge that we're facing. So I thought I might start by just giving a little bit of historical context of like where we are in galaxy formation. And I realized when I was thinking about this that galaxy formation, you could argue, is exactly 100 years old this year. So what happened 100 years ago is that Hubble measured the distance to Andromeda and showed that that galaxies were things outside the Milky Way. Okay, so we have our galaxy, and there are other galaxies. So that was the knowledge 100 years ago. And so, you know, there really wasn't there was a theory of the formation of the Milky Way before that. There were lots of debates about that. They were a little confused. But, okay. So, I mean, you could say it kind of maybe started to accelerate more like 50 years ago. In the sort of late 70s, we started to measure the first galaxy scaling relations. Okay, so some of those galaxy scaling relations are things like the Tully-Fisher relation, which is a relation between the luminosity or the baryonic mass of a galaxy and its velocity dispersion. The Faber-Jackson relation, which is, similar relation for elliptical galaxies, right? Relation between the luminosity of an elliptical galaxy and its velocity dispersion. Okay. So, actually, I missed a step. I wanted to go one step back to Hubble and mention that Hubble also said something else about galaxies, right? 3 really important things that Hubble did: expansion history of the universe, the fact that their galaxies are outside the Milky Way, and the Hubble sequence, right? So basically the idea that there's ellipticals and spirals and a whole sequence here. You could call this Hubble sequence, in modern terms of machine learning, kind of the first latent space of galaxy formation. Okay, so we've been talking a lot about that in this workshop. So what do I mean by that? Basically a way to compress the information in galaxies into a smaller number of dimensions. You might measure lots of properties of galaxies, but those properties of galaxies are correlated with each other. And so actually this Hubble sequence, as we now know, is also a sequence in many other things, right? Is also a sequence in the star formation rate, the age of the stars, not just the morphology. Okay, so that was kind of the first sort of thing. These kinds of galaxy scaling relations were probably telling us something about the gravitational physics that was putting galaxies together. These were actually measured before the establishment of our modern cosmological model, which is CDM. So that was, maybe 40 years ago. So we had the establishment of the idea that the matter density would be dominated by cold dark matter, some particle that really forms structure hierarchically, and that's the key feature of CDM. That structure forms from small things first, which then merge and grow to become bigger things. Actually, there were some sort of modern models of galaxy formation that came before CDM, White and Reese, for example, which had gas cooling in a halo. But really then, I would say modern galaxy formation started shortly after the formation, the establishment of CDM. You can think of these early models of galaxy formation that really started to form galaxies in cold dark matter halos, like, Blumenthal et al. Paper. And then, increasingly over these next sort of, maybe 35 to 25 years ago, these models started to develop a lot more, sort of early hydro simulations, work by Neil Katz, Lars Hernquist, that did these lovely hydro simulations that actually had lots of elements of modern galaxy formation theory in them, most of the modern elements. And I'm going to get to the sort of core picture of this in a minute. Also, Rachel and many others developed a methodology called semi-analytic models, which didn't try to solve all of the equations of hydrodynamics, but tried to do things a little bit more computationally cheaply, a little bit more schematically, but still trying to write equations for what was happening with the gas and the stars. We could say that about 25 years ago was the establishment of our current cosmological model, lambda CDM. And I mean, this model, as you all know, has gotten very increasingly precise over the last 25 years, but not really changed. And because it's gotten more precise, we've gotten a much more detailed picture of how structure forms in this model over the last 25 years. And so the key thing that happened around here is we started to have simulations with sufficient resolution to actually get dark matter halos and their substructures. So that was an important thing that happened. And we started to have statistical samples of galaxies. So I wrote my second paper on a sample of 1,000 galaxies at redshift 3. Actually, my first paper was on 13 galaxies at redshift 3. So that was around this time, right? The first kinds of redshift 3 galaxies, these Lyman break galaxies. And then actually around the same time was the first very large sample of low redshift galaxies, starting with Sloan, which has actually continued over the last 25 years, quite incredibly. And we discovered more scaling relations, right? We discovered, for example, the black hole, the M sigma relation, which relates the mass of a black hole to velocity dispersion, the mass metallicity relation, relations between specific star formation rate and stellar mass and redshift and how that changes over time, right? These kinds of things came about. And the other two kinds of theoretical developments over this time period is that these hydro simulations, I would say really in the last 5 to 10 years, have gotten much more realistic. So we could say that these things sort of have much more realistic galaxies, certainly not perfect yet, but getting much closer. And the other thing is that we have started to combine this lambda CDM simulations with these statistical samples for the kinds of galaxy models that are really sort of looking at the statistical connection of galaxies and halos. So the simple list of these are things like what you might have heard of, the halo occupation model that just tells you how many galaxies does a halo have as a function of its mass. Okay, there's more complicated versions of this, which I'll say more about. And both of these has really developed quite a bit over the last 5 to 10 years. And of course, thinking to the future, I think we really have a data revolution that we're kind of in the midst of, but certainly is going to accelerate. So just to spend a few more minutes on this cosmological model and the galaxy formation model. Let me just use this part of the board. Okay, so in the simplest picture to talk about what our theoretical framework is, right? We have a cosmological model, which essentially you start with some kinds of cosmological parameters, right? We have, omega matter, omega baryon, omega lambda, omega neutrino. We have the size of the fluctuations, sigma 8, whether they're bigger or smaller on different scales, and we have the expansion history. So simplest cosmological model. And what does this do? Well, if you have a nice computer, these parameters alone and just gravity enable you to make really detailed predictions for structure formation. And those predictions are very rich. They're computationally challenging, even for a given cosmological model, to do on the very widest range of scales. But they're very rich. So, we find, I said, that halos form hierarchically. You've got a set of mergers. So this is over the last 13 billion years. Halos forming over time. And this model tells you exactly how this happens, at what rate these things merge. It also tells you about their spatial distribution or their power spectrum, right? How these objects are, how the matter is distributed, but also how the halos are distributed. It tells you how many of them there are, right? It tells you, how many halos there are as a function of mass. It tells you, so how they're clustered. Sometimes we talk about the power spectrum. Sometimes we talk about something called the bias, which just is how clustered they are compared to the matter distribution. And more massive halos are more clustered with respect to the matter distribution than less massive halos, because they form in sort of, the high peaks. The massive halos sort of form up here, and the low mass halos form at lower density peaks. It also tells us about how halos accrete mass over time, right? So it has this merger tree, but you could also look at how does this most massive thing grow over time? And, that's something that we can predict really well from these simulations. Okay, so we have this really rich set of predictions, also the internal structure. Okay, and now we have a galaxy formation model. If we imagine a halo in isolation, which they aren't, but you know, some gas comes into this halo. The gas and the baryons are originally well mixed. The gas cools, falls to the center, and once it falls to the center, it can start to form stars. Okay, once those, there might be a black hole here. The stars actually, you know, different things happen. Some of them explode. They inject some feedback that can heat up the gas. The black hole also can heat up the gas. And so these are we're trying to understand all of these complex processes in the context of this halo formation. Okay, and if you put these two pieces together, that gives you really detailed predictions for lots of things about galaxies, right? How the galaxy population evolves over time, because we know the number of these things, and we could, with this model, we can understand how the number of halos is related to the number of galaxies. It tells you about the spatial distribution, because we can learn what galaxies form in what halos, and we have a prediction over here for the spatial distribution of galaxies. If at the simplest level you thought that the star formation rate was driven by gas accretion into the halo, then, you know, the gas accretion history should basically trace how the mass comes in, and that might tell you something about the star formation. So these are really intimately connected, the structure formation and the galaxy formation. And one of the things in how I think about this problem is one of the things we're trying to understand is how much of everything that we see about galaxies is driven primarily by what's happening with the structure formation, and how much of it is driven by the details of galaxy formation physics. Okay? So in my mind, that's kind of a fundamental question as we try to understand everything about galaxy formation. Okay, so now in that context, so that's kind of the theoretical landscape. Let's just talk a little bit about the data landscape that we're in now. We have a really incredibly rich data landscape that we are already living in, and that is coming soon, right? We have very large photometric surveys. Currently, things like DES, HSC, very soon, the Rubin Observatory, the camera is finishing this summer and shipping down to Chile. And for those of you who don't know, this camera, it's a 3.2 gigapixel camera. It's going to take a picture of half the sky every 3 days. And the idea is to do science with about 10 billion galaxies. Okay. Of course, it also takes a movie, so we'll see everything that changes with time. So we're not just taking a static picture. We're actually seeing things that change with time. We have spectroscopy. And, you know, right now I'm very excited about a survey called DESI, which just in the last 2 years has increased the number of spectra ever taken by humans by an order of magnitude. So we now have about 20 million spectra of galaxies and quasars. Already, I think, 5 million spectra of stars in the Milky Way. And we're only, you know, about a year and a half into this survey. So this is just the beginning. You know, of course, people are talking about many future surveys, both these kind of wide field spectrographs and also, you know, the ELTs that will be able to go much, much deeper. Of course, we have space telescopes like JWST, which is taking, you know, pictures of the earliest galaxies that have ever formed. Very soon, well, relatively soon coming, Roman, which has a field of view that is about 100 times Hubble. So now imagine everything you've seen with Hubble at roughly 100 times the rate that we have been able to do it so far. Very, very exciting. What's that? Yeah, no, that's right, Euclid. Euclid is launching this year, very exciting. They found a spare rocket to launch with, which is awesome. And I think also really exciting for galaxy formation is the new ways that we're going to have to see the gas. So that includes things like the cosmic microwave background. which is actually now a beautiful lensing survey. It also tells us about the gas around massive halos. Radio surveys, which can measure H1, and also fast radio bursts, which can measure the gas around halos. So we have just a really rich and exciting landscape that's really kind of coming. I should have mentioned X-ray, of course, as well. New telescopes being proposed in the X-ray that will actually be much more sensitive in the regime that matters for galaxy formation. Okay, so we have a lot that's coming in this context. So what do we want to try to do with our models of galaxy formation so that they actually do meet these data, right? So I think ideally we want, some models that are fundamentally informed by the basic physics. And we want these models to really be informative. But we also want these models to be sort of flexible so that when we actually try to fit the models with the data, we get sort of unbiased answers. Okay. We want these models to be able to make predictions for these very large and large dimensional and multi-wavelength data sets. And really, ideally, we want to be able to use all of the data we have. Or we want these models to be able to predict the things that we see. Now, maybe we don't actually care about all the data, but at least we want to use all of the informative data. And that might be an important piece of this. And I think we're trying to do two things that are related but a little bit distinct. One is essentially in the context of a given model that has parameters, we want to really be able to do robust inference in like a statistically meaningful way, right? We want to be able to say, here's my parameters, here's my data, here's how I have constrained the parameters of this model. But we might also want to learn new things, right? We also, might want to get new insight. Maybe our model is wrong. Maybe there are things going on with galaxy formation that were not in my model. And so I think we're trying to do both of these things in this context of thinking about how the models and the data meet each other. Okay, so thinking about these things, sort of this continuum from like physics-based informative models to flexible, unbiased models, right? Ideally, you would like to be able to do that all at once, right? That would be your goal. And unfortunately, none of the models that we have right now are of that kind. We can't do all of this at once. We're not there yet. We've developed a bunch of approaches in galaxy formation, or I would say approaches for going from a cosmological model to the properties and spatial distribution of galaxies. Okay? And those models sort of are on a continuum from sort of more physics-driven to more data-driven. And in my view, from where we are today, this whole spectrum has actually been quite useful in making progress in understanding things. And so, on the more physics-driven side, we have, full hydro simulations, where you try to do this with as much resolution as you possibly can. You try to put in the fundamental physics as much as you know it, but we still are trying to do this over many, many scales. And so even in this case, we are always making choices of some parameters that are sort of not directly simulated, right? We're not yet at the point where we can simulate a galaxy star by star. And so there are always some sort of parameterized subgrid models that still have some parameters. On this sort of much more data-driven side, we have sort of statistical kinds of models for how galaxies and halos are connected. So one example is something called halo occupation, or even with even less assumptions that only makes predictions for the linear regime, we could just talk about bias models. And and then there's some things in between. Okay, so sort of still trying to do hydro-like approaches, but much cheaper are these things called semi-analytic models. Maybe going one step further this way. So in this case, we're just making assumptions about those host halos here. In this case, we're just making assumptions about the relationship between, say, the galaxy overdensities and the matter overdensities. And we can make one more assumption so there's a kind of approach called subhalo abundance matching that basically doesn't just use the host halos, it also uses the substructure that is predicted by simulations. And so you're making sort of one more assumption, and then we can actually go sort of in between here, a new class of models which I call sort of empirical forward modeling, where you assume the full merger history of the dark matter halos, but not very much of the physics. So, an example that I worked on is a model where we just make a basic assumption that the star formation rate of a halo is related to the mass accretion rate. The star formation rate of a galaxy is related to the mass accretion rate of a halo, and we just do statistical matching with large data sets. Okay, so, this is a whole continuum here. We're much more physics driven. These are much less flexible, so they may or may not match the data. These are much more flexible, and so you may be able to do more robust inference with these kinds of models and really infer the parameters. They may or may not be flexible enough, but they're probably more flexible than this. But we may lose some physical insight as we go in this direction. Right? Here we actually know what's happening with the gas cooling and the star formation, and the black hole feedback, all of this, right? And here we don't know anything about that. We're sort of looking somewhere in between. Okay, so this is the kind of range of approaches we have because we can't do this, right? Okay. Okay, good. So let me just come back to what we are trying to learn. Let me see where I am with time. Okay, not a whole lot more time. Okay, so let me come back to this picture here of what we are trying to learn. And I would claim that it might be useful to kind of break up the things we're trying to learn as the parts of galaxy formation that are fundamentally driven by structure formation. Right? How many halos they are, how are they clustered, how do they grow over time. The parts of galaxy formation that are fundamentally driven by gas, stars, feedback, black holes, all of what we put under the label of galaxy formation physics. And then maybe there's a third category that's more like systematics in our data, random fluctuations, or uninformative features. And it may be that what you think is uninformative depends on your science goal. We've talked a lot about that actually at this meeting, right? It may be that galaxies have a transient feature that doesn't matter at all to understanding the global distribution, but if you're trying to understand that transient feature, you might care. So that's an important thing. Okay, so that's sort of big picture, I would say. We're trying to learn basically these two categories of things without worrying about this category of thing. Okay, and let me just, without writing on the board, give a few more details of, some of the more some of the more detailed problems that we've been talking about at this workshop. So just to give a few examples, right? How can we learn, essentially, how can we use all of the galaxy observations we have to learn about fundamental physics? Not galaxy formation, but to learn about cosmology and the nature of dark matter. So that's one set of questions. You know, that can be a challenging set of questions. You know, we have another set of questions about what does feedback do to the matter distribution, right? How does the feedback change, you know, the global matter distribution? We have another set of problems, say, characterizing the star formation histories and the stellar populations of galaxies. Another question, what do the billion stars that we have measurements of in the Milky Way tell us about its formation history? How do we put all of those pieces together? What determines galaxy morphology, right? Which parts of this picture really matter for galaxy morphology? And what determines the spatial distribution of galaxy properties? And I actually think, in my mind, that last question is actually really interesting because many communities think about that question using very different language. So this question of, you know, what determines the spatial distribution of galaxy properties, some people think about it in this biased language that mostly focuses on large scales. Some people mostly focus on how galaxies are related to their dark matter halos. Historically, this was a field where people studied this. Actually, I forgot to write on my historical thing here. You know, the first things like Butcher-Ohmler effect in '84, right? Looked at, you know, kind of looked at the fact that there were blue galaxies in the field, red galaxies in clusters, and that evolved over time. That was not in the context of dark matter halos. We still see papers that have those kinds of discussions that are not in that context. So in my mind, thinking carefully about the theoretical framework you're trying to connect to is really useful in trying to separate out these problems. Okay, so I want to just spend a little bit of time talking about how do we separate these problems most usefully? And I don't have an answer to this. This is what we have been talking about a lot in this workshop. But I did have a useful conversation with Josh Peak today that was helpful. And you know, crystallized some ways that I think about this. But, you know, sort of historically, we've often had this thing where we have a theory, and we use that theory to make predictions. And we take some observations, and we use those observations to sort of, you know, have some interpretation of the observations, and then we try to compare these things and see whether they match. And if they match, we win, and if they don't match, we adjust our model, right? Okay, so, I mean, let me just give you a really simple example. Simple example is, you know, the stellar mass function of galaxies, number of galaxies as a function of stellar mass. This is kind of an interesting one because stellar mass is neither really directly predicted from the models, nor is it directly measured from observations, right? We don't actually measure stellar mass. We measure luminosities. We measure, you know, luminosities in different bands. We try to infer, we make some inferences about the initial mass function of stars, and we try to infer this thing. So we have, you know, this thing in our simulations, and we have this thing in our observations. And the problem is that when they don't match, we don't really know, were we missing physics over here? And was it the cosmological model? Was it something about our feedback? Or we don't know whether were we missing systematics in our data, or we didn't observe some galaxies, or we observed some galaxies but we inferred the wrong IMF. So all of these kinds of things can be problems in this data model comparison. And this is a really simple example of the stellar mass function, but almost anything you can think about in galaxy formation has some characteristics like this. Because the reality is that none of our models are really quite at the stage where they are truly able to go all the way to the observations. Okay, so that's the state of affairs that we're in, and we've been in, but I think we are moving in another direction where we start with a theory and we make predictions in sort of this, maybe you could call it the stellar mass star formation rate kind of space, and then you try to make better predictions, which are really for something more like simulated data. So I've done a lot of this work myself to try to make realistic models that go as close to the data as we can. We've used these quite a bit in cosmological inference. And then, you know, the observations here, you're still going to meet somewhere in the middle. You're not going to go directly to the observations. I mean, maybe you still have this step, but, you know, maybe you can go a little bit closer, right? And how close you can go depends on how good your model is, maybe, but also how close you should go depends on what you're trying to do. And I think this is where a lot of the art is, and we've actually had a lot of sort of implicit and meta discussion about this in the last couple of weeks, and I expect there will be more. But I think, so people, I'm like one of the oldest people in this data-driven conference, and so the young people in this conference know a lot more about modern techniques than I do, and they have lots of fancy techniques for lots of inference from data, okay? And I'm just going to, I think I'm already running short on time, but I will mention just a few of the things, of the places where we've made advances, kind of both going this direction and trying to understand what, you know, so actually going back to this comment about the Hubble sequence and the latent space, maybe you don't want to go all the way to the observations, but you want to go to the part of the observations that really matter. So maybe you want to go to, you know, the smaller dimension version of the observations that are going to be most informative about your theory. Okay? And that's where I think we can actually use some of these new techniques. So I think there's two ways broadly that we can use the new generation of machine learning techniques, which I expect will be continuing to evolve very rapidly. And so I'm going to first just mention a few of the ways that we've used them for this part of it, and then I'll mention some ways that we've used it for this part of it. Just broadly, right, this part here is still quite a complex computational challenge. And I would say on this part of the diagram here, we are mostly using machine learning tools as a practical tool to speed up our calculations in efficient ways. And so I can give you a couple of examples. So just in the regime of dark matter simulations, people, instead of simulating every cosmological model they want to simulate, they build an efficient grid of cosmological models that effectively span, you know, say their 7-parameter space. You can probably do that, depending on what you're trying to do, with maybe 40, 50 kind of simulations, depending on your accuracy. And then you can actually build just efficient interpolators, usually called emulators here, that then tell you, okay, now from my 40 points in parameter space, I can effectively tell you what is the full distribution of matter and the properties of dark matter halos, and maybe even their accretion histories and their spatial distribution as a function of cosmological parameters. So that's something that's really accelerated over the last few years. I think it's actually been quite effective. People are just starting to do that with hydro simulations. So several people in this room have been part of a project called CAMELS, which has actually, for the first time, really done a suite of hydrodynamical simulations, still relatively low resolution, still, you know, not at the volume you'd like for cosmology, but starting to explore parameter space there. There's been a lot of improvement in how we're doing statistical inference on other kinds of models. So, you know, the version I told you about earlier, this kind of empirical model, that was, I think, probably the first model where we really were very clear, here's the data we're using, here's the model parameters we're constraining, and here's some posteriors in that space. People are starting to do that much more with different kinds of models and different kinds of data. So I think that's really effective. And we're also using these machine learning tools to really speed things up very effectively along every step of this chain. So one thing that is being increasingly done is, because this is a complex multi-scale problem, you know, you simulate one part of it at high resolution, and then you paste that on to you know, larger boxes. And that's, you know, you have to be very thoughtful about this. And, you know, I worry that this is it's a very complicated chain. It's got a lot of art to it, and how you put together the pieces. It feels a little bit Baroque. It's not really what one would really love to do if one could solve the whole problem. But we're trying to get there faster. And I think we have a lot of tools to speed up this whole chain. Then I think, you know, on this side of this, sort of going from observations to latent space, there's a lot of progress in this, and many people in this room have been drivers of that progress. So, you know, there are ways to compress the data, you know, to take, you know, many millions of spectra and say, okay, this can actually be compressed. So there was a recent work that shows that, you know, a 6-parameter autoencoder can describe essentially all of the Sloan spectra. There was really nice work on outlier detection, also done by people in this room, looking at, you know, taking all the Sloan spectra and saying, you know, which hundreds of these are the weirdest of these, and then you can learn some new physics from that. You can go on and follow up the weirdest ones and see what they're doing. And there's been some interesting today we heard the statement made that no new physics has been learned from latent space. So I think that's it's an interesting claim, and it's interesting to think about whether we have learned new physics from doing this or whether we will. I think it is probably true that we have not yet learned any new scaling relations from this approach that we didn't learn essentially mostly by plotting x versus y. I mean, there were a couple more complicated ones even in 3D with the fundamental plane, but maybe it's that we don't know how to think beyond 3D. I think that actually might be part of the problem. I don't know that anyone's really given a compelling physical thing that's like, here's an n-dimensional thing in galaxy formation that I learned from my autoencoder that now teaches me how galaxy formation works. If you know of one, I'd love to hear it. So I think that's interesting, but I do think we are making a lot of progress in both of these directions. And I think one of the things that I'm hopeful of, in addition to the machines sort of speeding up, helping us speed up this part and getting to our ultimate goal of galaxy formation faster than we would have otherwise, I hope they might be able to tell us how far we should take this arrow. And kind of coming back to this picture of, you know, trying to understand which parts of this model do we care about and not care about, right? It may be that we can use that to help us learn, you know, which part is just systematics or random fluctuations or uninformative information, and which part is really telling us about the physics that we want to learn. And, you know, exactly whether that will be successful or not, we'll see, but I'm actually just extremely encouraged by all of the exciting ideas I have heard from young people at this meeting. And I think we have a lot of fun work to do in this field in the next decade. So I'm going to end there.
So we get it on, yeah, this way it goes on the recording. Thanks. This is really interesting. So I'm not an astrophysicist. I have a comment and a question. The comment is I'm actually publishing a paper probably in the next week about learning new physics from latent space. So it is, you can do it. Information bottlenecks are the key. And you know, if you keep an eye out on arXiv and HEP-PH, probably you'll find it there. The question is, so as a computing person, when I think of big data for astrophysics, I think of SKA. You didn't mention that one. Was it just left off the list? Or?
It was, I mentioned radio and I didn't mention the specific radio things, yes.
Okay,
so
that's
yes.
also one of these big
Absolutely.
Okay.
No, SKA is very exciting. Yeah.
Thanks.
Muon Collider people, questions?
Yeah, definitely Muon Collider people go first.
Yeah. Okay, Michael.
I'll ask you a question. Actually, I could ask you a question about this at home, but
That's okay.
why don't I ask it in public? So let me ask you about bias. So bias is something that people talked about in the 80s when you guys were first learning about this process of galaxy formation.
Yeah.
So this is a totally empirical measure, the level at which you form observable structure.
Yes.
Do we know anything about what happens like below the level of the density of matter that we would consider the bias that would produce galaxies? Is this something that we're also learning about from these new data sets? Yes. I mean, so the bias that we talked about at the beginning, you know, in my first papers 25 years ago, and many people in this room helped develop, you know, is just thinking about sort of on large scales, what's the clustering of halos or galaxies compared to the clustering of matter. And in the local universe, on large scales, it's approximately 1. They're approximately the same. At high redshift, you know, the peaks collapse first, and so high redshift galaxies are very biased. But we know, in some sense, what's beneath that because it gets revealed as the universe evolves. So that's one answer to your question. Another answer to your question is that when I talk about, so we're usually talking about collapsed objects when we talk about bias, but as we start to map the entire intergalactic medium, we're actually no longer fully looking at collapsed objects, and then we can actually map out the whole cosmic web. And in fact, there's a program here at the same time really thinking about the details of the cosmic web, which is partially made of collapsed objects, but partially not. And so that's, you know, that is certainly part of what we are trying to understand and what is being revealed by these new data.
How many of these scaling laws, the old ones, the ones are explained? How
many are explained? I'd say some, but not all. I mean, you know, these sort of classical ones are mostly about dynamics. I think those are reasonably well understood.
Understood by simulations that reproduce them? Or
I mean, okay, good question. Reasonably well produced by simulations, but also, you know, you can make analytic arguments based on, you know, the virial theorem for why they exist. Some of the other ones, I think, you know, for example, the mass metallicity relation you can produce in simulations. I think I wouldn't necessarily go as far to say that we have a fundamental understanding of exactly why it has the shape and form that it has. To give, you know, just to give a couple examples. Black hole mass relation, right? We can measure it very well. We definitely don't understand it.
Yeah. So those are sort of challenges to the community?
Absolutely. Yeah. I mean, I think, you know, that's part of what we hope to do in this grand model is actually understand those things better. And maybe some of these new data will inform that usefully. I mean, one thing that I think is becoming increasingly clear is that, you know, there are a lot of degeneracies if you only look at the galaxies. And so I think we have a big opportunity in the next decade with being able to measure the gas much better than we have before.
that we will be able to break some of those degeneracies and really understand in much more detail what's going on with the feedback, because it will really be obvious in the distribution and the temperature of the gas.
So thank you very much. It was a very nice summary, very inspiring. I wanted to ask you something, because what leaves me a little bit skeptical sometimes is the fact that you put their theory as something that we actually do know. And probably, like, analytically, there are many things that are known, but the problem is that they are difficult to implement numerically. And often the way they are implemented numerically is then twisted according to match observations, right? So the level of prediction that they make, you don't know how correct it is. And so it is like...
Yeah, so I completely agree, and I had started this thread but didn't quite reconnect it at the end. So when I was talking about what are we trying to do eventually, right, I said that I think of what we're trying to do with these models as like two kinds of things. One is, for a given model, can we robustly infer the underlying parameters? That's like one version of that. But, we also want to test that model and maybe break it. And so, we also want to really, have the opportunity to gain new insight that breaks this theory. Maybe we get lucky and it tells us a new scaling law that, that informs us really clearly, but maybe it just tells us this model is not good enough and we better try harder. So I completely agree. We don't have a full theory. And so that is absolutely part of what we need to be doing.
I have an extremely naive question, since you said the word breaking theory, which is that, from 100,000 feet away, as I am, it all seems incredibly nonlinear, complicated, feedback, all this crazy stuff.
Yeah.
Is there some observation that could actually break the theory, or are there always enough, are there qualitative things that even if you can't sort of, predict things precisely, there are qualitative correlations, or something that could convince you it's wrong? Or are there always enough knobs that you can turn that you can sort of accommodate anything you might find?
Yeah, I think that's a very fair question. I believe there are observations. We can think of some specific examples of, some of these theories are more schematic than others, right? This part of the theory, we kind of know what's happening. There's a very clear set of parameters. That set of parameters tells you what the matter distribution looks like. In this part of the theory, some of the things are kind of more schematic, right? It's like, okay, I've got a black hole. Here's how it gets its energy into the intercluster medium. And here's what happens, when a supernova explodes. Here's what happens to the gas and whether it just heats up or whether it heats up and gets blown out. But, both of those are examples where there are observations that can distinguish between those two stories. How much is it getting heated? How much is it getting blown out? And I think, especially with some of these examples, as I said, I think, really the revolution in being able to measure the gas density and gas temperature is going to really help us distinguish the actual physical processes and remove many of the knobs that we currently have. So I expect 20 years from now, the kind of observations that we have will be much more distinguishing of the physics than what we have now.
I want to focus for a second on what you have brilliantly labeled wiggly between simulated data and observation. you know that Peebles' Xi, he called wiggly. So that wiggly is extremely important because you're describing a compression of the observations onto a space, which I now understand we call latent. But does machine learning actually give you guidance on the nature of what that space should be? Or is it something that you're sort of imposing from above?
Yeah, there are definitely people in this room who are more expert on that question than I am, but I think it can give you guidance. My view is that it really can give you guidance on like what is the dimension of that space, what is the most useful version of that space for describing the data. Now, I think where we want to be eventually is informed by both directions. So if we think about being informed from the left, we want the most useful version of that space that actually tells us something about the physics. And if we only think from the right, we want, you know, just the most compressed version of that space. And whether or not those are the same is not obvious. But I think that's where the art is. I don't think I don't think the machines will fully tell us that, but I think they can help.
So I think what you're describing is PIN, physics informed, compared to blind.
Yeah.
And I completely agree with that, but that isn't being done as much as it might be, although I know it's coming heavily.
Yeah, I agree. And I think, I think there's a lot of progress in that regime, as I said, where those arrows go, how far, and how much information is coming from each side. I think that's where that's actually, I think, a lot of what people are thinking about and really intellectually engaging with as we think about how to make use of these large data sets.
So I'm one of those people who are working with these latent spaces, actually. But I'm in the opinion that at the end of the day, what we want is to actually just simulate the observables directly without just having a intermediate latent space. So it just feels like another space that it might be useful. So I think we should just simulate what we can observe, the exact realizations, and that would be the end. And would like to hear your opinion on that.
Yeah, so I guess the question I have for you is where do you stop? Do you want to truly simulate everything about the data?
That would be the best, right? No?
Not necessarily. Well, okay. Is it per unit effort? Insight per unit effort, maybe. Maybe
you can do everything.
Yeah, I mean, sure, if I am an all-knowing being and I can just do that, then I might choose that, but I'm not, and I have a finite lifetime. And so I would personally like to get the quickest insight per unit effort. And so I think there is a real decision to make about how much we simulate and how much we, try to, I don't think that the people doing hydro simulations, for example, are the same people who usually think carefully about detector effects. So that's just an example. That doesn't mean they can't work together and build a full end-to-end simulation, and that is happening actually. But I think I think there is a lot of art there, and it does depend on how much time you have and how many graduate students.
Great place to stop. Thank you, Risa.